Good afternoon and a warm welcome to our webinar. It's now 1 minute after 3 o'clock Central European time, and it's time for us to start this webinar. So this webinar has got the title, Demonstration of an Interlocking Design Automation Solution, and this webinar is hosted by Prover. So before I hand over to today's speaker, I just want to make sure that you all understand that you have this possibility to ask questions. There is a specific functionality in GoToWebinar that you can use for asking questions during the webinar. You can check your control panels for this question mark icon, and if you press the question mark icon there, you can type in your questions. So you can also ask your questions whenever you want, and we will do our best to answer your questions in the end of the webinar. So please take the opportunity to type in your questions, because we really do have experts with us here on the webinar. When you type in your questions, the rest of the audience will not see your questions, so that we are the only ones that will see the questions coming in. So I think it's time for me now to hand over to our speaker today, Gunnar Smith from Prover.
Thank you, Lars. So, thank you all for joining today, and good afternoon or good morning wherever you are. So before I get started, just a very short words about myself. So I'm currently VP Sales at Prover, but I've been with Prover since 2000, so for quite some time in various roles, starting out as a software engineer, working on a product development for formal verification tools, and since then in various roles, and often involved in many of our client projects in the railway signaling and train control domain. So today, the main topic is the demonstration of our Prover iLock tool suite that will cover automated development, test, and verification of rail control software. And in this particular case, it's software for a small interlocking that we will look closer at. And in the end, I will also give some recommendations for what I think you should consider when you are thinking about a signaling automation process for your rail control projects. I expect that this will take about 30 minutes, perhaps a little bit more, and then we will get to the questions that you might pose during the demonstration and presentation. So please remember to ask questions. So the product suite Prover Trident, which Prover iLock is a part of, is depicted here, and it's called Prover Trident because it consists of 3 main parts. It starts with specifications of requirements in the PySpec language. So this we sometimes refer to as a generic application where you capture all the rules that you want your systems to follow. We will not get into that much detail on that today, but I will mention it a little bit throughout the presentation and demonstration. In this case, it will be used to specify requirements on interlocking signaling systems, but it can be used for many different kinds of interlocking systems, and also more complex compound systems of systems like CBTC system, for instance. Then we have the Prover iLock tool, which is the centerpiece of this demonstration. It can be seen as an application engineering tool where you take these generic requirements expressed in the PySpec language and create specific requirements for a system configuration. And from these specific requirements, you can generate application software in some coding language, and you can do automated testing and formal safety verification, as well as generating a wide range of documentation on your system. And this will be the main focus of the demonstration today. Then finally, we have Prover Certifier, which is a formal verification tool that is used independently of Prover iLock. So you can use it to generate safety evidence for your system that is independent on the tool that developed the system, Prover iLock. So it takes the generated software and the configuration data of your system together with the safety requirements and verifies that this software that you have generated fulfills these requirements. And of course, the same process can be applied even if you have systems that you have developed in a more traditional way without using Prover. You can still apply this kind of safety verification. And when I say formal verification, what I really mean then is that it's an automated verification based on mathematical methods, so that you actually can trust the result to 100%. It's not like testing where it's limited to a set of test scenarios. Instead, it covers the entire possible state space by mathematical reasoning, and this by an automatic algorithm. So it gives you very good trust in the safety. So what do we want to achieve with such an automated development process? Well, we want to improve the way the rail control projects of today are delivered and developed. So in particular, we want to increase the interoperability and reliability in these systems. We want to make sure that when you get the first delivery of a new rail control system, it should be on time and with the correct functionality. And we think that automation in both code generation, but in particular the VNV part is very important to achieve this. And as you know, rail control systems have a very long lifetime, typically maybe 15, 25 years or sometimes even more. And the maintenance of these different subsystems that build up the complete rail control system, it can be quite challenging over this time. And we think that reducing the life cycle cost is a key goal, especially when you look at the cost savings. That's typically where you find the really big cost savings. And also that automation tool can be a great help in that. It will help you maintain your systems, and it will support you when you want to change requirements and functionality over time, so that you don't end up with obsolete systems that are very difficult to update. So what we will do in this demonstration, we will focus on what we call the specific application process, or SA process here. And we will do it for an interlocking, a fairly simple interlocking. And also interlocking is a good example because it's a relatively isolated part of the signaling system, but still capable of demonstrating many of the benefits. So here, a specific application is basically an individual interlocking, whereas the generic application contains the requirements and the functionality that any interlocking system should follow for, let's say, the same railroad or the same metro. So we will start by configuring a station in this Prover tool, but we will not do the full process, of course, of defining all the requirements. So we will start with something that already exists, some what we call a predefined signaling principles. We will then instantiate these requirements based on the configuration and demonstrate how simulation can test the functionality of the system. We will apply the formal verification to prove the safety of the system, and we will look briefly at how you can generate code to execute on a safe computer in the field, basically. And when it comes to this process of dealing with the requirements, we will look at a few examples of what the requirements might look like in the PySpec language, and also look at what might happen if we change some of the requirements and redo the verification and simulation. So, as mentioned, we will use some predefined signaling requirements here, a predefined generic application that we have developed for training and demonstration purposes. So it's some fairly simplified signaling rules, you could say, but you should still be able to see how this could map to a more realistic and more complex signaling application. So the main object that you need to understand in this context is the main signals that we use and their aspects. So the top unit in these signals is the sort of main aspect. Red means stop, and then yellow is a restricted aspect used with when you have points in reverse position ahead, so kind of proceed with caution. And then green is for higher speed moves. And the bottom aspect is function for distant signaling. So if the next signal is at stop, it will display red, and if the next signal is restricted, it will display yellow. And finally, when it displays green over green, it means that you have no reverse switches ahead, and the next signal on the route is also unrestricted, so you can proceed at full speed, basically. So some very simple signaling aspects here to get a basic understanding of how it works. So I will now switch to the Prover tool. And when I open the Prover tool, it consists of a main window where you will do the configuration. And as explained, it depends on this generic application where we have specified the rules. And we will now create a new project based on some existing rules. So I will give the project a name, and I will do a small siding location. So I call it siding demo. Then there's a path to where to store it, and then I need to select which package I will use for these requirements. And then we have this demo package to use. And then this is another setting I just need to change. So I will now create a new project called siding demo, store it at this location using this package specifying the generic application and all the signaling rules. So it will now load, and it will now have performed a consistency check of all the packages we're using. So down here you have a long list of different packages where most of them have a fingerprint so that it checks that the integrity of the packages are correct. And then there are a few without fingerprints, which are the actual demo packages that are in sort of development state so that we can change them. All the others have fixed version numbers and are basically a set of utility packages that we build them on so that you can have a hierarchy of package using like a library of existing requirements and so on. You can also add some additional information about the project here, who the author of the project is, date, version, and so on. But we're happy with this as is, so I just click OK. And we now have like a drawing canvas here where we can create this specific application configuration. So for this simple demo, I will only draw a track layout and place the objects. In a more realistic example, there might be additional configuration data that you might consider importing from various tables and so on. And you might even, for complex interlockings, already have an existing database with a track layout and so on that you want to import into the Prover tool instead. And it supports that as well. But here we will create it from scratch in this editor. So I have the different objects here. And again, these objects are not built into the Prover tool. They're part of this generic application. So you specify what objects you have, and then you specify the requirements on these objects. So we have tracks, obviously, which is kind of a built-in. You have track circuits, track joints or delimiters, basic directions, so you can talk about the direction of objects. We have a location object, we have main signals, and we have shunting signals. So my intention now is to create a very simple siding location. So I start by drawing a straight track, and then I will add the siding by just drawing it like this so that it creates a switch here, and then I will add a name for the switch. And sorry about that. Like that, and then I will create the additional tracks on the siding here, like this, and name the extra switch like that. So we now have the basic track layout and the two switch objects that were kind of created automatically when we had diverging tracks. Next step is to add these joints so that we can place signals. And then I will use a feature here called repeat new object, because I will place quite a few of these joints. I will just name them. These names are not maybe that important, but so I will just give them a D for delimiter and oh, sorry, go back to that one later. So obviously you have to take care so that you don't try to create names with the same, or rather objects with the same names, because then it will complain. I will have to rename it later. So I have basically added these delimiters now so that we have an area surrounding each point or switch. This one should be D3 instead. So we have an area here and an area here, then the two areas in between and the ones going out from the main interlocking. And I will now create track circuits for these. So you see that when I select the track circuit, it will select the area depending on where I am on the canvas with the mouse. So again, I will just create some simple name for these, like 1T and so on. Of course, in a real project, you have some proper names for these objects. And the last one should be 6T. So now we have these track circuits associated with the areas. Next thing to do is add the main signals. And again, I will have add only main signals here in the most simple way, having one main signal protecting each possible entrance to the switch area. And these I will call S1, S2, and so on. And then I will right click here to change the direction of the signal so it faces the point. It's S2, S3, S4. And I'm careful here to place these signals on directly on the joints, as you can see by the blue line here. And we actually have a built-in check in this particular demo package that you place signals this way. But that's of course something that might depend on your generic requirements, how you are allowed to place the signals. But placing them on the joint is quite a common way to do it. So now I'm done with the majority of the objects. I just need to add the directions. Here they are mainly used to be able to name different objects. So I have a direction to the right that I call E for east, and then one to the left that I will call W for west, maybe. Just move that a bit so that you can read it. And finally, I have a location object. In this simple case, the location object is not that significant, but you can imagine having a larger project with a number of locations and a number of objects that you need to associate with different locations. For instance, you might have multiple controller objects if you have a large interlocking that takes care of the logic for different parts or areas of the interlocking. So I will now save this project. And what I have done this far is simply creating a configuration based on the objects that are defined in our generic application. And all the requirements are still in the generic application. And now I want the tool to create the specific requirements. So for instance, it will now generate all the possible routes according to the rules that we have. And it will generate all the logic requirements for each specific object here. So for each signal, for instance, it will generate specific requirements. And I will do that by clicking here, T here to go to the tools phase. So we call this the layout phase where we configure things. And the tools phase is where we do the simulation, verification, and code generation. So now the tool is creating the specific requirements for this configuration. And for a small, simple interlocking like this one, it takes only a moment. But even for a large one, it's only a matter of a minute at most. So it's not very complicated process of doing that. So now what has happened? Well, the tool has created the logical program representing this interlocking based on the requirements that we have in the generic application. We can start by just taking a quick look at this program. If we go to the tools menu here and select the programs viewer, we see a number of programs up here. This is called the siding area code container. This is the main program. Then there is something for the testing and verification and another internal program. For more complex interlockings, you might have different programs implementing the same interlocking, like having perhaps a non-vital part and a vital part, and as mentioned, you can also have multiple controllers. But here we have one simple program with inputs, equations, outputs, and some timers. And you can see the definition of these equations on the right here as some kind of ladder logic or in a text-based Boolean format here. And this, as is common with interlocking systems, they are typically Boolean, but you can imagine also having other signaling systems like zone controllers for a CBTC, for instance, where you have also some integers or even floating point numbers and arithmetic operations on that. Then that will be included as well. But right now we are limited to the Booleans in this example. And the next thing I want to show you is the simulation. And the simulation comes in two flavors. One that is simulation of test cases that are part of the generic specification. So it contains generic test cases that the tool has then instantiated particular for this interlocking that can be automatically executed, and you can generate a test report. Or you can do like manual or interactive testing in the tool. So I will show you that first, and then I click this interactive simulation button up here. It will launch the simulation or the simulator module, and it will run a predefined test sequence to initialize the system. And here you see that it is running in real time. And it starts here by waiting for 60 seconds to do some initialization of some timers that are in the system. But fortunately, it has an efficient algorithm for compressing time so that you don't have to wait for 60 seconds, of course, which would be quite tedious. So I will now minimize this, and you see now in this view here that all the signals are at red. If you can see it, I'll make it a little bit bigger. The switches are indicated to be in the normal position. And if I right-click on an object, I have some settings I can do. I can set inputs, or there are even some, in some cases, predefined procedures or tests that I can run. But here I will request a route to lock, and you see on the track layout there, it's highlighted which route we're talking about. So I will request this route from the S6 signal onto the siding ending at signal S3. So it's now request, and you see that the switch moves. When it becomes locked, the route locks as indicated by these green arrows, and the signal in this case turns yellow. It's yellow here because we have a switch or a point that is not in its straight position, if you recall the meaning of different aspects. And now I can also simulate things like a train entering this route by just clicking on the track circuits, and you see that the signal goes red and so on. So this is basically for testing manual behavior of the system when you want to find out how it works, or you want to debug some issue that you have. And you can see now that the route has released, and the switch is no longer locked, so I should be able to request it back to the left position here, and then it moves. So this is a quick introduction to how you can use the tool to just play around with the system and test it. I will then show you the built-in or scripted test. So I will open the simulator module. And here we have a few test cases that are defined in this generic application. So we have a test for a main route. We have a few different ones. This first one tests that routes are released correctly after the traversal of a train. And if I click run, the tool will automatically run through all these tests. And if I click here, you can see that for each test there is a number of instances. So the test name up here, that's sort of corresponds to the generic test from the generic application, and then the tool have automatically created each individual test for each route here. So you don't need to bother by how to map these generic tests onto the specific configuration that you have. So that's done automatically for you. The next part is the formal verification. It looks similar. You have a list of generic requirements. For each requirement, there is a number of instances corresponding to the specific objects you have in this. So again, they're split per route. If we look at this first requirement, it has an identifier, and it says here that if two different routes include fully or partially a common track, these two routes are never being locked simultaneously. So this is like the natural language specification of the requirement, and then we also have a formalization of this in the PySpec language. And finally, the tool has created the specific requirements corresponding to this based on the different routes we have in our interlocking. So if I click run here, all the requirements turned green, and you can see here that there were 310 requirement instances, and they were all proved valid. In case that we had falsifiable requirements, that is violated requirements, you would be able to go in and debug them here. And I will soon show you a little bit more about that. So the simulation is basically used to test the functionality of your system, that it does what you want it to do. And the formal verification is used to prove or check that it doesn't do anything bad. So you test that you have the functionality you want, and you make sure that nothing bad will ever happen, like corresponding in real life to trains running into each other or running at too high speed or whatever to derail. And then, as mentioned, to use this application in a real signaling system, we must of course export this in some piece of software that can be compiled and run on your logic controller or computer in the field. So we have what we call a coder module. And the Prover tool supports a number of different languages and interlocking or signaling target platforms. So it can be, in this case, we have chosen to export the application as more generic C code that you can compile on a normal computer, but it also supports different standard formats for PLCs like structured text, and it supports many different interlocking platforms that have their proprietary programming and configuration languages. So of course it exports the actual logic of the system, but also the I/O configuration and the communication data and so on. So in this case, I will just quickly show you what the exported code looks like, and it opens a folder here, and it has generated the different C files that are needed that you can compile. And the exact details of this file is not very interesting for us now, but just to show you what it looks like. It's basically the same logic that we saw before, but in another programming language that you can compile instead. And one thing that is important here is, if you recall the Prover Certifier tool I mentioned, when we use that, we want to make sure that the application that has been generated or exported from the Prover tool is actually safe. So it will actually need to use this exported software rather than the model that we have in the Prover tool, and it will translate this this format into a model and verify that against the requirements. So you know that the code generation has not introduced any errors or so on. You can check that it actually fulfills all the safety requirements independent of the Prover tool. So I'll close that one. So those are the basic modules that you normally use in Prover. You have the simulator, the verifier, and the coder. And I will now quickly show you a little bit on how these PySpec requirements, part of the generic application, looks. So out here you have a view that says project and package. Projects are all the specifics that we have out here. So if I look at design, for instance, I have different objects like the different signals. Each signal has a set of routes and so on. So it's all the specific data, but you also have a folder or a tab package that contains the specification packages that are part of the generic application that we were talking about. And this demo application package is split up into design rules, safety rules, and test rules or requirements. And it also has an object model called OM here, which gives you the common interface between these different parts. So it's important to split design requirements from the safety and the test so that you know what you are talking about. And it also makes it easier to build a safety case around the safety requirements, not mixing them up with the design requirement. So the design requirement is actual implementation. So we will look at one file here in the PySpec language. We'll take the one that implements a switch. So we'll open that here, and it will just launch a text editor with some syntax highlighting. So these are documentation strings, and then you have different functions here. And the PySpec language is, you can compare it to a programming language that is sort of tailored to develop rail control software. It's built on a few common software engineering practices, like you have classes, so some kind of object orientation with the possibility to inherit and so on. And it's also built on predicate logic, so you can efficiently express the requirements. So first here, you have a set of functions for checking different properties of the object, the object here being a switch. And these properties can either be dynamic, like this one, detected left. It depends on the actual state of the system, so it reads some kind of input probably from the switch. Or they can be more static, talking about the actual configuration, so maybe which track circuit is the switch contained in and so on. Then you have a section here called equations, which is where you implement the actual design. So these equations will show up in the code that we generated, the C code, in a different format then as well. So if we look, for instance, that we have a locked equation, and you have a text here telling you that what it means. The switch locks when it could be dangerous to throw it. So kind of a very brief explanation. And then there are the different conditions for when to lock the switch. Then we have the throw left equation, which we'll look a little bit at now. So what this means is that this is a negation, if you can see it here, and this is logical and this is logical or. So the switch should be thrown to the left when it's not locked, it is not already left, and there is no request for it in the opposite position, the right position. And finally, there must be either a left request coming from the sort of traffic management or control system, or there is a requested route that needs this in the left position. So now I will introduce a small error in this this equation, and we will look at the impact when we run the tests again. So to throw it left, it needs to be initiated by a command to throw it to the left. But let's say I made a typo here or a copy paste error and said that it was right here, and I save this file. Then I can go in and take this project here that I configured and reload it. That means that it basically reads these PySpec files again from the generic application. And it takes a few moments to load this because it's again checking the integrity of the packages and so on. And then we're back in this layout phase, so I need to instantiate the requirements again. So now we can think of what the impact of this change might be. So I'm going to run the simulation and the verification, and we will see if there are any failing test cases or any failing safety requirements. And I will start now when this is instantiated to run the verification. And as you can see, it turns out all the requirements passed. So there is still no violated safety requirement. And I will come back to that and try to explain that a little bit later. First, we'll run the simulation. So here we see some red tests. That means fail. So we have 7 failing test cases, and we can see here that these are for particular routes, the S1 to S4 and the S3 to the exit here. And if I double click one of these, it will bring up a debugger, which I can run. That will show me a little bit more details about the failures here. So here, the red here means that you have a statement that is failing. So here we are checking that the route becomes locked after you have requested it. But that doesn't happen. And if you can see it here on this gray line, you see that the switch here is still in the normal position. It was never thrown, so the signal can't clear. So that's also why you don't have a problem with the safety requirements, because the signal cannot clear, which means that if the signal cannot clear, the system is safe, since you're not allowed to pass the signal. But it doesn't really mean that you can use the signal. So in this case, you cannot get the signal to display proceed aspect. And we can run the test case to this particular point and try to examine it. And then we can look at the different variables. For instance, if we find the variables for switch 1, we can try to figure out why it's not in the left position. And this might be a little bit hard to follow here, but we can just try to go through it. So the switch is not left. So it hasn't moved to the left. So checking here that now we can find here that the throw left equation is not true. So we don't have a left request. And that you can see here is that you only have the left request from the HMI here. You should have the one that I deliberately removed here to request it right. So we have one that checks first that it's not requested to the right by route, but then we only have the left and the right is missing, which is exactly the error that we introduced. So we can close that one. And if we go back to this PySpec and fix this one, we go back to left, it should work. But then I want to show you also something that's impacting the safety requirements. And then we can look at the locked equation, which is typically very critical for the safety, that the switch cannot move when it's not supposed to. And the first part here is talking about the track circuits that this switch is on, that they need to be vacant, otherwise the switch should be locked. Then it should also be locked if there are some routes or flank protection or front protection paths that requires the switch to be locked, but we don't need to get into that details. I will just remove or comment out this line and see what the impact of this is. So we can guess that it should now be possible to move a switch when the track circuit is occupied, so basically when it's under a train, which is of course not good. So hopefully we will have some safety requirements that catches this. Otherwise we have missed some requirements on the safety side. So again, I have reloaded this application, and I will again instantiate the requirements for this particular interlocking. And we'll run the verification. So now we have actually 2 falsified requirements. You can see here that it's the switch requirement, so it fails for both these switches. And if I double click, it will bring up what we call a counterexample, basically a scenario where the requirement is violated. And you can see here, a little bit hard to follow maybe, but that it expects this 2 T-track circuits to be vacant, this one, but it's not. But still, the switch has gone from not being placed right to actually being placed right, which is a bit bad. So you can try to find out how this can happen. And if you browse down here, you will eventually encounter the locked equation. And this one is up when it should be down, and you will need to examine it to find that the check for vacancy here is missing from this particular equation, which of course might take a while to understand if you didn't already know where to look. But anyway, this is how you can go about debugging these failing requirements. So I will just put that back. And then if we reloaded everything, it would, of course, again, be back to normal with the successful tests and verification. So that's it for the very quick demonstration, but hopefully you got the idea. And if you want to know more about it, just ask a question or let me know and we can help you with that. So I will now just go back to the presentation here and summarize what we have actually done this far. So we looked in particular to what we call the SA process, the specific application process. We configured a simple interlocking or sliding location. And in this very simplified demonstration, we only needed to add the objects and a track layout. And we used an existing generic application with all the signaling requirements. In a real life example, you might have more complex configuration data and you might import this, as mentioned, from existing databases or file formats that you may already have. We show that you could use simulation to test your system, and it's good to have automated simulation, but also simulation that actually automatically uses generic test cases so that you don't need to manually specify each individual test for your object. And it's key to a design automation process to have good simulation so that you can run it early to discover issues in the requirements that you have. So normally you would want to write or develop test cases in parallel to developing the design so that you can always test it. And it's the same for the formal verification, where we simply could prove the absence of any error, or when there were errors, as we saw, it would show you which requirements were violated. And this is also something that you should do iteratively as you develop the requirements, both for the design and safety. Code generation is just a push of a button, basically taking the instantiated requirements and turning them into some format that can be used for compilation and do the to run the application in a real system. If you do not want to generate code, you can of course also use the simulation and verification to verify and test your existing code. If you want to use another process for developing the code, then Prover supports that as well, to import code instead. And the generic application or GA process, we just touched very briefly upon it, showed what happened if we modified requirements. So we use simulation to show functional impacts of a design error. So in this case, we saw that signals could not clear if the switches were not requested to move, but the system was still safe. And we used formal verification for other design errors to show when a safety critical bug was introduced. In this case, that a switch could actually move under a train, which is not really good. And while we're not focusing on this process to develop generic application today, I'd still like to share some recommendation and thoughts on how to go about developing them. So normally you would start by, of course, determine which requirements you have. So you would do this, and this is not really different if you're using a design automation process or any other process that you normally use. You need to gather and analyze all the requirements you have, speak to the users, look at the interfaces, rules and regulations, and so on. And then you need to document this so that you have some idea of what to implement. And you need to find the principles for how to configure, implement, test, and verify each individual system. And a key part here that we promote is the use of what we call an object model. And an object model, it specifies clearly the different interfaces for the physical objects, but also for the different parts of the requirements, so that you can have design requirements developed independently of the test requirements of the test cases, because they have a common structure, the object model, that they can refer to. So it's basically a description of all the objects you have with their main properties and relations between objects, interfaces like input outputs, how they communicate, and so on. But it does not actually deal with the implementation of the specific requirements. So that is instead done for the individual specification for the design, the test, and the safety. And when you establish the requirements, you typically do that in a few steps. So you have these natural language requirements that you can discuss pretty much with anybody involved. They can understand them. Then you need to formalize them. You need to formalize them so that they can be used by automation tools, but also to remove any ambiguities, and so that you can validate them. So you can basically use this process also only for validating your requirements, even if you're not going to use it to develop specific application software. You can test and validate your requirements using prototyping with specific system configuration in this process. And of course, you don't do this just from the top to the bottom. It's an iterative test-driven process where you try out your requirements. And finally, of course, we stress that you should use automation tools in doing this. You should take your principles, formalize them into this requirement specification, and use automation tools to configure your application, generate the application software, get the safety evidence using formal safety verification, and produce the test reports for the functional test of the system. And of course, there will always be some tests that you cannot not only do in the tools, but you will need to use on the actual installation of the system. And for that, you can also generate test instructions from these tools so that you can repeat the test using the actual hardware. And it also supports hardware in the loop testing, where you can use actual physical objects in the simulation. So if you think this sounds like a great idea, like we do, to use design automation when you implement your rail control systems or when you specify them, please do not hesitate to get in touch, and we can discuss this further. And with that said, I think that was my last slide. So let's see if we have any questions from the audience, maybe.
So thanks for the demonstration and the presentation, Gunnar. We are now going to move over to a Q&A session. So please take the opportunity now to type in your questions using the functionality in GoToWebinar for asking questions. And we have received a couple of questions that we will start with, but please don't hesitate to type in your questions, and we'll do our best to answer them now. So let's start with the first question, Gunnar. So can you please provide more details about the tools qualification as per EN 50128? Do you understand the question?
Yes, sort of. So the key tool that is relevant there is the Prover Certifier tool, which is classified as a T2 tool. So it's a tool that is used to independently check the development process. And that is a tool that we are certifying according to this standard, so that you can build a safety case around it. And then you can use it to prove that regardless of the development process used, the end result, that's the application software, will actually fulfill the safety requirements. So that's the T2 tool for an independent verification tool. Then the Prover iLock tool itself is classified, if I recall the standard correctly, as a T4 tool, I think. I might be wrong on that. That is actually used to generate or create the application. But as we have this Prover certified tool that will guarantee to find any safety issues introduced by the Prover iLock tool, it's not the Prover iLock tool itself is not safety critical in that sense. Hopefully that answers the questions. Otherwise, I'll be glad to elaborate more on that.
Okay, thanks for that answer. And we move on to second question. How is the behavior of wayside objects handled in the simulation?
Right. So in this simple application that we saw here, we didn't have that much interaction with wayside objects, but we had some very simple models, for example, for the point machines. When they were given a request to move, and that would correspond to an actual output from the interlocking system to the wayside object, then there was a simulation model causing this switch to actually move, simulating that it takes a few seconds to move this point machine. And it was sort of implemented as a program in the simulation environment. And there can be, of course, be more complex such modelings of the objects that we need to consider. And there are also interfaces so that you can connect the Prover iLock tool to external devices to use, for example, actual switches or simulation or emulation of point machines and other objects in the simulation environment. So you need to have some kind of model representing those objects.
Okay, so we hope this answers the question, and we'll move on to a third question. Can we use any other language instead of the customized PySpec language?
So the PySpec language is the language used by the Prover iLock tool for the specifications. So that's what we recommend. Of course, how you might have different process for how you go about creating these specifications, and you could envision also having translators, of course, from existing languages into PySpec. So it's not something that we have done a lot, but I guess it could be done if you have some preferred language where you already have specifications that you want to reuse, or if you have a more high-level specification language giving parts of the design, you can perhaps incorporate those into the PySpec language. But Prover iLock itself supports the PySpec language only for the specifications.
Okay, and there is some more questions coming in. Okay, fourth question. Can we use event B for specifications? Can we use event capital B for specifications? I wonder if this is clear enough for you, Gunnar?
Yes, it is. So that's another sort of specification language or formal language, you could say. And I mean, the short answer is no, because you need to use the PySpec language. But of course, it could be possible to, as I said, do specific translators and so on if you have maybe a full design or a partial design that you want to use. But it's hard to say in general how feasible that would be to use event B. But it could be possible, yes. It would have to be examined from case to case, I guess.
Okay, so if you're in that situation, you can of course contact Gunnar afterwards and maybe have a separate discussion about that. So we still have a couple of more minutes left until we have to close down the webinar. We don't have any more questions at the moment, but if you have, well, here's another question coming. So can your model asynchronous systems? Can your model asynchronous systems. Do you understand the question, Gunnar?
Yes. Yes, I would say in principle. So it doesn't really perhaps apply to the simple application like the one we saw here, but there's nothing preventing you to model that in the PySpec language.
Okay, good. So yeah, we don't have any more questions right now, but if you have more questions, you still have a chance. See if there is any more questions coming in. While we're waiting, we'll just inform you that you will receive an email tomorrow with the contact details for Gunnar, so you can get in contact with him and Prover after the webinar. You will also receive a link to a recording of the webinar so that you can look at the webinar afterwards or share the webinar with others. So that will happen tomorrow. So there's another question coming here. How much training time is needed to learn PySpec? Or PySpec, sorry.
Yes, of course, difficult to answer in general, but I could say that to use Prover like we did here with existing specification is of course much easier. That's typically just a matter of a few days of training and a little bit of practice. When it comes to PySpec, it depends a lot on what you're used to already. Let's say you want to learn how to specify signaling requirements in PySpec. If you already have the sort of Rail domain knowledge and you have basic understanding of some programming languages and some concepts, then it might not be that difficult. We have some training programs for that. Typically, they would run for a period of 3 days times 3, you could say. So you would learn it over some time. Yeah, so it's kind of hard to just answer that question, but it is more complex than just using the Prover tool. But we have the training programs to help you with that, of course.
Okay, yeah, time is running out and it's time for us now to close down this webinar. If you have more questions for Gunnar and for Prover, you can always come back with those questions and ask those because you're gonna get the contact details in the email tomorrow. So Gunnar, thanks for the presentation. I think we need to say a warm thanks to everyone that took their time to join this webinar this afternoon. Maybe some final words before we close down the webinar?
No, just again, a big thank you for all of you for attending and for your questions. And if any further questions pops up, please just let me know and I'll be happy to answer.